Welcome to section 4.2, inverse functions. Objective 1, determine whether a function is one-to-one. We've already seen different ways of representing functions. The following illustrates two different functions using mapping. Okay, so we have a grouping on the left, a grouping on the right, and then the arrows signify the mapping or where the value on the left matches to a value on the right. So although both relations above are functions, okay, there is a difference between them. In the first figure, no two elements from the domain correspond to the same element from the range. However, in the second figure, different elements, didn't need an S, different elements in the domain correspond to the same element in the range. The mapping in the first figure is a one-to-one function. The mapping in the second figure is not. So a one-to-one function is defined by this definition. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function, then f is one-to-one if f of x1 does not equal f of x2. Okay? Put another way, a function f is one-to-one if no y in the range is the image of more than one x in the domain. The figure below illustrates the distinction among one-to-one functions, functions that are not one-to-one, and relations that are not functions. So A here is representative of a one-to-one function because every x in the domain has one and only one image in the range, meaning it maps to only one y. B is not a one-to-one function because y1, right, y1 is the image of both x1 and x2. C is not a function because x1, all right, has two images, y1 and y2, meaning it maps to two different y values. Okay, for this example, we're now going to determine whether the following functions are one-to-one. So for the following function, the domain represents the ages of 5 males and the range represents their HDL, good cholesterol scores. So we have our age here as the domain and our HDL as our range. Well, in order for it to be one-to-one, every x must have exactly one y, and multiple x's can't have the same y. Okay, so if you see here, 41 and 53 both map to 35. So the function is not one-to-one because there are two different inputs, 41 and 53, that correspond to the same output, 35. Okay. For B, we have a set of ordered pairs. Okay. So -3 maps to 5, -2 maps to 3, -1 maps to 1, 0 maps to -1, and 2 maps to -3. Note that there are different x values, and each x value maps to one specific y value. No two x values have the same y. So the function is 1-to-1 because every element let's change that to every distinct. Let's change those words. Every distinct input corresponds to a different output. There we go. Awesome. So when a function is represented by an equation y equals f of x, for which the graph of f is known, a simple test called the horizontal line test can be used to determine if f is 1-to-1. Now the theorem for the horizontal line test states that if every horizontal line intersects the graph of a function f in at most one point, then f is 1-to-1. To help visualize why this works, consider the figure to the right. Notice that the horizontal line, y equals h, intersects the graph at two distinct points. First point is x1, h, and the second point, x2, h. Okay, so that's right here and right here. Okay, since h is the image of both x1 and x2, and x1 does not equal x2, f is not 1-to-1. Based on the figure, we can state the horizontal line test another way. If the graph of any horizontal line intersects the graph of a function more than once, the function is not 1-to-1. So for each function in this example, use its graph to determine whether the function is 1-to-1. Okay. Now for A, we have f of x equals x to the 6th power. Okay. This graph is going to take the shape of a parabola. So if we plug in 1 or 0, we'll get 0. If we plug in 1, we'll get 1. And if we plug in -1, we'll get 1. So let's just use those for now, those points, and draw our parabola. Okay. All right. So to determine whether this is 1-to-1, we're going to draw a horizontal line, just like similar to the vertical line test. Okay. This is the line y equals 1. It crosses the graph at the point -1, 1, and at the point 1, 1. Therefore, this function is not 1-to-1. Okay. For B, we have g of x equals x to the 5th power. So let's plug in some points. We plug in 0, we'll get 0. We plug in 1, we'll get 1. We plug in -1, we will get -1. Okay, so our graph looks something like this. Oops, I totally missed that point. Let me attempt that. Let's start from the top. Maybe that is easier actually for me. There we go. Alrighty. So we're going to now draw a horizontal line. And that's through the point 1, 1. That is the line y equals 1. Let's draw another horizontal line. That is the horizontal line y equals -1. And that's at the point -1, -1. Okay. So notice that the function here for g of x equals x to the fifth has two horizontal lines through it, and it only touches the graph at one point. So we would say this is a one-to-one function. Okay. So notice in the function in part B, it is an increasing function. So it will always have different y values for unequal x values. So it's increasing, reading left to right. So if we start here at the bottom, reading left to right, we see our graph is increasing. Therefore, we're going to have different y values for unequal x values. So that leads us to this theorem that states a function that is increasing on an interval I is a one-to-one function on I, and a function that is decreasing on an interval I is a one-to-one function on I. Okay. Objective 2, determine the inverse of a function defined by a mapping or a set of ordered pairs. One-to-one functions y equals f of x have an important property. Corresponding to each x in the domain of f, there is exactly one y in the range because f is a function. And corresponding to each y in the range of f, there is exactly one x in the domain because f is 1 to 1. The function represented by the correspondence from the range back to the domain is called the inverse function of f. The definition of the inverse function states that suppose that f is a one-to-one function. The correspondence from the range of f to the domain of f is called the inverse function of f. The symbol f to -1, but it's not actually a power. All right, we're going to talk about exactly what that means. It's a representation. So this doesn't mean f to the power -1. So we're not like evaluating it at the power -1. It represents the inverse function of f. So this is how we represent inverse function of f. So this is the symbol for the inverse function of f. So when you see this, we're not saying f to the power -1, although that's what it looks like. We're actually saying the inverse function of f. So this is the symbol for it. And this is used to denote the inverse function of f. In other words, if y equals f of x is a 1-to-1 function, then f has an inverse function where x equals the inverse function of y. Okay, so we've gone through a lot of verbiage, but let's now go into an example. But before we do, we have a caution. Okay, So f of x to the power -1 equals 1 divided by f of x. So this is different, right, than the inverse function of f. So this is not the same thing as f of x to the power -1. They're not the same thing. So we have to pay very close attention to what our problem is asking us. Okay. When you have this -1 in the power location, it is representing the inverse function. However, if you have a -1 outside a grouping, like f of x here is within brackets, then it's referring to the exponent rules for a negative exponent. Okay, so just keep that in mind when working with functions. So in our example here, we're asked to find the inverse of the function defined by the map. Let the domain of the function represent hours worked, and let the range represent the gross income in dollars. Find the domain and range of the inverse function. So we see here in our function that each input in the hours worked corresponds to one gross income output in the range grouping. So our inverse function is going to be the opposite. So our domain is going to be the gross income, and our range is going to be the hours worked. Okay. So the gross income inputs in this case would be the outputs of the function. So 300, 360, 450, and 600. Hours worked would be 10, 12, 15, and 20. 300 would map to 10, 360 would map to 12, 450 would map to 15, and 600 would map to 20. Okay. So using this, we can now state the domain of our inverse function and the range of our inverse function. So the domain is going to be all the values in our first grouping here. That's going to be our domain. And the second grouping here, the hours worked, will be our range. So that would be 300, 360, 450, and 600. Our range would be 10, 12, 15, and 20. So if the function f is a set of ordered pairs in the form xy, then the inverse function of f is the set of ordered pairs yx. So you're just flipping the domain and the range. So let's do that in this example. So find the inverse of the following one-to-one function, and then state the domain and range of the function and its inverse. Okay. So for the function f, let's first state the domain and range, which will allow us to easily then state the inverse function, its domain and range. So the domain is going to be all of our x coordinates. So that would be -2, -1, 0, 1, and 2. Our range is going to be all of the y coordinates. So that would be -11, -8, -5, -2, and 1. Now to state the inverse function, we're actually going to switch the domain and the range. So what was the domain of the function is now the range of the inverse function. So that would be -2, -1, 0, 1, and 2. Now the range of the function is now the domain of the inverse function. So that would be negative 11, negative 8, negative 5, negative 2, and negative 1. Okay. All right. Objective 3. Obtain the graph of the inverse function from the graph of a one-to-one function. So suppose the point AB is a point on the graph of a one-to-one function y equals f of x. This means that B equals f of a. It also means that a equals the inverse function of f of b. So BA is a point on the graph of the inverse function. In the figure to the right, notice that the line segment with endpoints AB and BA is perpendicular to the line y equals x and is bisected by the line y equals x. Therefore, the point BA on the graph of the inverse function of f is the reflection about the line y equals x of the point AB on the graph of f. This leads us to the following theorem. The graph of a one-to-one function f and the graph of its inverse function are symmetric with respect to the line y equals x. So once the graph of f is known and the graph of the inverse function of f can be obtained by reflecting the graph of f about the line y equals x. This can be done by switching x and y in all ordered pairs on the graph of f. For example, if the point 2, 5 is on the graph of f, then the point 5, 2 is on the graph of the inverse function of f. Similarly, if the point negative 1, 3 is on the graph of f, then the point 3, negative 1 is on the graph of the inverse function of f. So the graph in the figure here shows a one-to-one function, y equals f of x. We are now asked to draw the graph of its inverse function. Okay, so if I take the points on our graph that are given to us and I switch the x and y, I'll now have points for my inverse function. So while we graph, I want us to keep in mind that the graph of the inverse function of f is the reflection of the graph of f of x about the line y equals x. Okay. So let's plot our points for our inverse function. So we're going to take each point one at a time and switch the x and y coordinate. So let's first take 3, 4. If we switch the x and y, we'll get the point 4, 3. So 4, 3. So that's this point right here. And we can label it 4, 3. Our next point is 0, 2. So if we switch the x and y coordinates, we'll get 2, 0. Okay. And our third point is negative 1, negative 3. So if we switch the x and y, we'll get negative 3, negative 1. Okay. And so now let's connect the dots. Okay. And so now we have the inverse function of f. Note that it is reflective about the line y equals x. Okay. Objective 4. Verify that a function defined by an equation is an inverse function. So suppose f is a one-to-one function. Then f has an inverse function. Since we obtain the graph of the inverse function by switching x and y coordinates on the graph of f, it makes sense that a similar relationship exists between the domain and range of a function and the domain and range of its inverse. Now the figure below shows the relationship between the domain and range of f and the domain and range of the inverse function of f. So from the figure, we can see the following. The domain of f equals the range of the inverse function of f. The range of f equals the domain of the inverse function of f. This simply means that the inverse of a function undoes what the function does, and vice versa, as shown in the following illustration. Input x from domain of f is applied to f of x. If we apply to the inverse function of f, the inverse function of f of x will equal x. If we take the input x from the domain of the inverse function of f and we apply it to the inverse function of f of x, then we apply that to the function of f of x, we will then get x. So in other words, the inverse function of f of x equals x, where x is the domain of f, and f of the inverse function of f of x also equals x, where x is in the domain of the inverse function of f. Okay. So this allows us to verify that two functions are inverses of each other. So let's verify that the inverse of g of x equals x to the fifth is the inverse function of g of x equals the fifth root of x. So first we're going to find the inverse function of g of f of x. So the inverse function of g of x, we're going to input g of x, which is x to the fifth, and we're going to take that expression and substitute it into the inverse function. So that'll be the fifth root of x to the fifth. So when we simplify that, that will get us x. Then we are going to find g of the inverse function of g of x, and that will give us g. The inverse function of g is the fifth root of x. So I'm going to substitute that into g of x. Now when I simplify, I get x. Okay. So I verified now that the inverse function g of x is the inverse function of g. Let's do another one. We have f of x and we have the inverse function of f of x. So first we're going to take the inverse function of f of x. So f of x is 3x minus 5. We're going to substitute that into the inverse function. So that's 3x minus 5 plus 5. Then we can simplify. So 1/3 times 3x will get us x. Then we'll take f of the inverse function of f of x. So the inverse function is 1/3 times x plus 5. So we'll substitute that expression into f of x. So that's 3 times 1/3 times x plus 5 plus 5. All right. Oh, plus 5. Yes. Oh, minus 5. Not plus 5. It's minus 5. Minus 5. Okay. So now we can simplify. So multiply 3 times this quantity, which will get us x plus 5 minus 5, which equals x. So we have now verified that the inverse function of f of x is actually the inverse function of f. So verify the inverse of f of x equals 1 over x plus 2 is the inverse function of f equals 1 over x minus 2. For what values of x is the inverse function of f of x equal to x? And for what values of x is f of the inverse function of f of x equal to x? So let's first find the domain of f and the domain of the inverse function of f. So both have or contain ratios, and we know that when we contain ratios, our denominator cannot equal 0. So we need to find the values of x that make our denominator 0. So for f of x, our denominator is x plus 2. So in order for that to equal 0, x would have to be negative 2. So the domain of f is going to be all x values except for when x equals negative 2. For the domain of the inverse function of f, we have 1 divided by x minus 2. Now the denominator for our ratio cannot equal 0, so that means x cannot equal 0. So the domain of the inverse function of f will be all x values except for when x equals 0. Okay. So now let's evaluate both of these expressions. So first we'll take the inverse function of f of x. So that will be the inverse function of f, where x is 1 divided by x plus 2. So we'll substitute that into the inverse function. Okay. And we can rewrite the first ratio. So that would be x plus 2 over 1. So we can just leave it as x plus 2 minus 2, and that equals x. Okay, so it can equal x provided that x does not equal negative 2. So we have to keep that in mind. Okay. Now f of the inverse function of f of x. So the inverse function is 1 over x minus 2. We're going to substitute that into f of x. So that's 1 divided by x minus 2 plus 2. We can simplify the denominators because the 2's cancel, so that gives us 1 divided by 1 over x, which simplifies to x. And this is provided that x does not equal 0. Because if x equals 0, then our expression would be undefined. Okay. All right. Objective 5. Find the inverse of a function defined by an equation. So recall that the graphs of a one-to-one function f and its inverse function are symmetric with respect to the line y equals x. This means that we can obtain the inverse function by interchanging the roles of x and y in f. If f is defined by the equation y equals f of x, then the inverse function of f is defined by the equation x equals f of y. The equation x equals f of y defines the inverse function of f implicitly. If we can solve this equation for y, we will have the explicit form of the inverse function of f. That is y equals the inverse function of f of x. So now we're going to go into finding the inverse of a function defined by an equation. So find the inverse of f of x equals 3x minus 5. And then we're going to graph the function and its inverse on the same coordinate axis. So when you're asked to find the inverse of a function, you're going to go through these 3 steps. Step number 1, you're going to replace f of x with y, and then interchange the variables x and y. This equation defines the inverse function of f implicitly. Okay, so let's do that. So we have our function f of x equals 3x minus 5. We are going to change f of x to y, so replace f of x with y, and then we're going to interchange our equation where x is now y and y is now x. So this is the inverse function implicitly. So step 2 says, if possible, solve the implicit equation for y in terms of x to obtain the explicit form of the inverse function of f, which is y equals the inverse function of f of x. Okay, so we'll take our implicit equation and now we want to solve for y. So we can, let's see, I'm going to switch my side so I have x on the right hand side. So then I have y on the left hand side. So now I'm going to add 5 to both sides and now divide by 3. Okay, so y equals 1/3 times x plus 5, or in other words, the inverse function of f of x equals 1/3 x plus 5. Okay, so now I can check the result by showing that the inverse function of f of x equals x, and f of the inverse function of f of x equals x. Okay. So once I'm able to show that, then I can graph my equation. All right, so let's quickly show that. So we're going to check our solution. So first we'll do the inverse function of f not times. Ooh, no, it is not times. We will take the inverse function of f of x. No times at all. All right, so the inverse function of f and then f of x is equal to 3x minus 5. Okay, so then we're going to substitute that into the inverse function, and our inverse function was 1/3 times 3x minus 5 plus 5. So the 5's cancel, which gives us 1/3 times 3x, which gives us x. All right, so the first part is true. So now we'll take f of the inverse function of f of x. So our inverse function was 1/3 x plus 5. And we'll substitute that into our f of x function. 1/3 x plus 5 minus 5, multiply by 3, and we get x plus 5 minus 5, which equals x, which is true. Okay. So now we can graph both functions. Okay. So let's graph our f of x function, 3x minus 5, because it's written in slope-intercept form. So our y-intercept is negative 5, and our slope is 3. So we'll go up 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 1, 2, 3. There we go. Over 1. And then we can connect the dots. Okay, we verified that it is that's not right. It's supposed to be 0. We verified that our functions are inverses. So this is 1, negative 2. So we can take each of these points and interchange the x and y's. And this is 3, 4. Okay. So 0, negative 5 is now negative 5, 0. 1, negative 2 is now negative 2, 1. 2, 1 is now 1, 2. And 3, 4 is now 4, 3. And so now we can connect our dots. And we can label. So this is, oh, I was right the first time. Negative 5, 0. Negative 2, 1. 1, 2. And 4, 3. Notice that our lines are reflections of the y equals x line. Awesome. So now this slide just summarizes the procedure for finding the inverse of a one-to-one function. So again, in step 1, in y equals f of x, interchange the x and y to obtain x equals f of y. This equation defines the inverse function implicitly. Then in step 2, if possible, you'll solve the implicit equation for y in terms of x to obtain the explicit form of the inverse function of f. Y equals the inverse function of f. And then in step 3, you'll check the result by showing that the inverse function of f of x equals x, and that f of the inverse function of f of x equals x. Okay. So for this example, we are asked to find the inverse of a function defined by an equation. So the function f of x equals 3x minus 1 divided by 2x plus 1, where x does not equal negative 1/2 is 1-to-1. We need to find its inverse function and then check the result. So step 1 tells us to interchange the variables x and y. So f of x equals 3x minus 1 divided by 2x plus 1. So I first will change f of x to y. That's my first step. Then I will interchange my x and my y. So I'll get x equals 3y minus 1 divided by 2y plus 1. Now for step 2, I'm asked to solve for y. So I'll start with my implicit equation, x equals 3y minus 1 divided by 2y plus 1. So to get y by itself, I'm going to multiply both sides by 2y plus 1 in order to get that binomial out of the denominator. Then I will distribute the x to each term within the parentheses, giving me 2xy plus x equals 3y 1. Now I'll get all of the terms that contain a y on the left-hand side and all of the other terms on the other side. Okay. Now the two terms on the left-hand side both contain a y. So I can factor out a y, leaving me with 2x minus 3. To get y by itself, I'll divide both sides by 2x minus 3. And now I have the inverse function of f, which is negative x minus 1 divided by 2x minus 3. Okay. Awesome. So step 3 is now to check whether both of these are actually inverses of each other. So our f of x, I'll write this at the top, was 3x minus 1 divided by 2x plus 1. And our inverse function of f came out to be negative x minus 1 divided by 2x minus 3. So if both of these are the correct inverse functions of each other, then both of these expressions that we need to check should equal x. So for the first one, we're going to take the inverse function of f of x. So f of x is 3x minus 1 divided by 2x plus 1. And I'm going to substitute that into my equation of the inverse function of f. So I'll have negative 3x minus 1 over 2x plus 1 minus 1 divided by 2 times 3x minus 1 over 2x plus 1 plus 1. Okay. Now I want to get common denominators in the numerator and denominator, so I'll be multiplying my constant terms, so that's negative 1 and plus 1, by 2x plus 1, so that I can eliminate the denominators. So this will get me negative 3x minus 1 times 2x plus 1. And then I'll have 2 times 3x minus 1 plus 1 times 2x plus 1. So now I can simplify the numerator. So I'll have negative 3x plus 1 minus 2x minus 1 over 6x minus 2 plus 2x plus 1. Okay. So let me just check this one more time. 3x minus 1, 2x plus 1. Yes. And, ooh, small mistake. I hope you caught it before I did. I just want to make sure, because my inverse is minus 3. So this should be minus 3. So these will be different values. Good catch. Minus 3. I was like, where did the 3 go? There we go. So this would be minus 6x minus 3. Okay, nice. Now we can combine like terms. So that's negative 5x over, these cancel, negative 5, which equals x. Yay, that's what we want. Woo, good catch. So now let's do the next one, f of the inverse function of f of x. So the inverse function is negative x minus 1 divided by 2x minus 3. So we're going to substitute that into the f of x function. So that would be 3. This is in whole parentheses. Okay, 3 times negative x minus 1 divided by 2x minus 3 minus 1. And then 2 times negative x minus 1 over 2x minus 3 plus 1. So I'll multiply my constants, negative 1 and plus 1, by 2x minus 3. So 3 times negative x minus 1 times 2x minus 3 divided by 2 times negative x minus 1 plus 1 times 2x minus 3. So I'll simplify. So I have negative 3x minus 3 minus 2x plus 3 divided by minus or negative 2x minus 2 plus 2x minus 3. Okay. Cancel out the negative 3 and 3 in the numerator, and then the negative 2x and positive 2x in the denominator. So that leaves me with negative 5x in the numerator and negative 5 in the denominator, which gets me x. Woo! Yay! That's great. Awesome. Okay, so if a function is not one-to-one, it has no inverse function. Sometimes, though, an appropriate restriction on the domain of such a function yields a new function that is one-to-one. Then the function defined on the restricted domain has an inverse function. So we're now going to look at an example where we're asked to find the inverse function of a domain that is restricted. So find the inverse function of y equals f of x, which equals x to the fourth, if x is greater than or equal to 0. Then graph f and the inverse function of f. Okay. So first, let's interchange the variables of x and y. So our function is f of x equals x to the fourth, which means y equals x to the fourth. So if we interchange, we're going to get x equals y to the fourth. Remember, provided that y, let me not go into the graph, because we're going to need that later. I'll write it under it. Provided that y is greater than or equal to 0. Okay. Now we want to solve for y. Okay. So solving for y, let's move y to the left-hand side, x to the right-hand side. So I just switched both sides, but they mean the same thing. So I'm going to take the fourth root to get rid of my power, and I will have y equals the fourth root of x. So my inverse function of f equals the fourth root of x. Okay. So if I were to graph this, okay, so I know that my function f of x is x to the fourth, where x is greater than 0. So if it weren't greater than 0, then it would be a parabola. But since x has to be equal to or greater than 0, my graph is going to look something like this. Okay. So if I'm now graphing the fourth root of x, where my y was greater than 0, greater than or equal to 0, it's going to look something like this. Okay. Note that it is reflective over the line y equals x. Okay. But let's finish off by verifying that they're actually inverses of each other. So graphically, we've shown that they are, but algebraically, let's show that they are. So my function f of x is x to the fourth, and my inverse function of f is the fourth root of x. So in the first one, inverse function of f of x to the fourth. So I'm substituting that into my inverse function. Will get me the value x. Okay, but it has to be the absolute value of x because x has to be greater than or equal to 0. Then f of the inverse function of f, so that would be f of the fourth root of x, which is what I'll be substituting into f of x. When I simplify that, I'll get x. Okay, and so I see here that both of these equal x. Yay! All right, that concludes section 4.2.